Okay, good afternoon, all of you. Welcome to this lecture of refrigeration air conditioning. So we are again meeting after several days. There was a long gap between these two lectures, this and this previous lecture. And I also see that strength is decreasing, so looks like I have to call their parents. So students see this final year exam are not going to be taking place in the next month. So nowadays their oral internal and external both they are taking place. Okay, so we don't know what will happen. So it was said that they will be exempted from the exams, but it is not the case. So they have to give the exams, and nowadays from yesterday their orals have been started today, and tomorrow there will be their project related oral will be there. So we are using this online platform to take the orals. So exams will happen. Okay, so it will be not like they will be exempted. They will happen. So the point is that we don't know what will be in your case. So please attend the lectures and be regular. So we don't know that if university asks for your online performance in the future, it may happen, right? Okay, so today we'll first revise because we are meeting after so many days. So first I will revise about this vapor absorption refrigeration system. And then today we'll derive the equation for the COP of this system, coefficient of performance. Then we'll take one or two numericals, and then one system remains, that is a lithium bromide system that we, if possible, will take today, or we'll keep it for our next lecture. Okay. So we are in this fourth chapter, vapor absorption system, refrigeration system. This was the syllabus. So we started with comparing it with VCRS, that is a vapor compression refrigeration cycle. A vapor compression refrigeration cycle consists of four major elements. First is evaporator, compressor, condenser, and expansion valve. So evaporator is the part which extracts the heat from the space. It is responsible for the cooling phenomena, and condenser is the part which rejects the heat into the atmosphere. To carry out this whole operation, or to create the pressure differences in the system, we need a compressor. So compressor uh, increases the pressure of the refrigerant, vapor refrigerant, which is coming from the evaporator. It compressor compresses that, and it increases its pressure to the pressure of condenser, right? So I have many times I have repeated this. So compressor works best if the refrigerant is in its vapor form. It should be dry saturated, or it should be superheated, but it should be in the gaseous form. If I talk about expansion valve should be it can handle only liquids. So the care is been taken that whatever refrigerant entering the expansion valve, that should be in the liquid phase. Okay, so then we are seen various types of VCRS in first chapter. Then we have solved the numericals also related to VCRS. Also, I have showed the examples or the system which are working on VCRS. So in one lecture we have designed one cold room which was designed to, which was supposed to store apples. In that case, we calculated the heat loads, and then we designed the system. Actually, we calculated the heat load, design and selection of the equipment. That was the next step, which we didn't take. Okay. So for your level, that heat load calculation is sufficient. If you go in the industry, if you do job in this refrigeration or air conditioning company, in that case, you will have to select the equipments. So there will be some companies. Okay, so if you are working in one firm and you have to design a system for a industry, you have, okay, in that case, that industry may release tender, then your company will fill that tender. So if you get that contract to design and install, or the engineering and procurement of that industry for their refrigeration needs, in that case, if you get that contract, then you have to do the heat load calculations. And then when selecting the equipment, suppose if you want hundreds of compressors, in that case you will release a requirement. So various companies, so there is Emerson, there is this Kirloskar, all they will give their quotation for the compressor. Again, you will select the compressor or you will approach the company which are giving you list price. So that way it will happen. You will select the equipments, and then when you go on actual site, There you will procure this arrangement. So whole system will be assembled. Then the testing will take place to test that whether it is actually extracting that amount of heat from the space. So finally, after the checking, we can say that we have installed and this system is okay to run. Okay. So after VCRS, what drawbacks in VCRS? It was first it was a compressor. So compressor means compressor is having various moving parts like piston and other arrangement. So in that case, a lot of noise and vibrations are generated. Also, that energy requirement for VCRS are very high. So considering these drawbacks, we move towards the VRS system. So VRS means vapor absorption refrigeration system. So before going to the VRS, I have explained you this phenomena of absorption. So you have already studied this in your high school, that absorption and absorption. This was in chemistry. So absorption means when a gas it is being absorbed, or that gas diffuses inside a liquid. All this, what you see on the left side, this figure. Here in this case, this gaseous particles, these are diffused inside the liquid. So this phenomena, what we call it as a absorption. But what you see on the right side, so if a liquid apply on solid surface, so it adheres to the surface. So as it adheres to the surface, it is called as absorption. So this is the good example for this is applying paint. जसं आपण भिंतीला रंग देतो त्यावेळेस काय असतं तर त्या कलरची एक पापडी तर तयार होते. तर असं नाही होत की कलर ह्या सिमेंटच्या भिंतीमध्ये ऍब्सॉर्ब केला जातो. सो इट डझंट टेक प्लेस. सो a thin film is generated on the surface of the wall. So that was the case of absorption. In absorption, that gas will diffuse inside the liquid. So as in our case, we are using aqua ammonia solutions. So in this case, whatever vapor ammonia is there in our system, it is being absorbed by the water. Also, I have showed you one video of ammonia fountain. So in that case, ammonia is being absorbed by the water. Pressure difference is generated. To compensate that pressure difference, water is ejected through a tube and we get a fountain. So those who did not see in last lecture, they can Google it, or you can see the videos on YouTube also. Ammonia fountain. Okay. So this was something about VRS system. So what is happening in this case? Whatever compressor part is there, so that compressor is replaced by absorber, generator, and a pump. Okay. So we are reducing that energy dependency on electricity. So in VCRS system, we have to depend a lot on local electricity. So in VRS, that their objective is to minimize this dependency on electricity. Okay. So where it is used, where the electricity is unreliable. So places where noise on the compressor can create disturbances. So we don't want that noise. Also, we don't want reliability on the electricity. So where extra or exhaust heat easily available. So wherever we can use solar heat or waste heat, in that case we can go for VRS system. So these were the components for the VRS system: generator, pump, and absorber. These three components will replace the compressor of the VCRS system. Then condenser, evaporator, expansion, and throttling devices. So these are common in both. And some other components like rectifier, analyzer, and heat exchanger. So what are these? We'll see today. Also, I have given this slight idea about this role of these components, but today we'll see in detail. And this was the diagram for a simple vapor absorption system. Why it is called simple? Because it doesn't contain rectifier, analyzer, and heat exchanger. So whatever very important components of the system that are shown in this diagram. Okay. So as you know, in simple VRS system, in that case, there are two circuits. Okay. So one is a absorber circuit, another is refrigerant circuit. So in this case, our refrigerant is ammonia and our absorbent is a water. So there are two parts. If I consider absorption, there will be an absorbent and there will be absorbate. Okay, absorbate म्हणजे तो की जो absorbent मध्ये dissolve होतो किंवा त्यामध्ये mix होतो. So absorbate and absorbent. So in this case, absorbate is ammonia, absorbent is water. So if I start with evaporator, so evaporator, what happens in evaporator? Heat is being taken inside, heat is extracted from the space. So water coming outside evaporator here, that will be a gaseous ammonia, a vapor ammonia. So that vapor ammonia is passed to the absorber. The absorber मध्ये काय असतं तर water असते. So that liquid water will absorb the gases or vapor ammonia. A good mixture is created. That mixture is called as strong solution. Why it is called as strong solution? Because it contains more concentration of ammonia. Again, this absorption phenomena. So this is an exothermic reaction. So some heat is being generated. Temperature increases. To reduce that temperature, we are using a cooling water system. Okay. So why we want to reduce the temperature here? Because lesser the temperature, greater will be the dissolvability. So if I maintain the temperature lower here, more ammonia will be dissolved inside the water, okay, absorbed inside the water. So then we get a strong solution. A strong solution is then pumped with their pump. Then it is passed to the generator. In generator, what happens? We are taking advantage of difference in boiling points. So that ammonia's boiling point is very less, and the water's boiling point is very high. So in that case, we are supplying external heat. So here we can supply with solar heat, or you can supply waste heat. So that is advantage of VRS system. We don't want to depend on electricity. So that we can use here. So though in this diagram they have said that steam or heating coil. So heating coil, obviously it will take electricity, but instead of that you can go for steam. Okay, so that steam you'll get from water. So you can boil the water with the help of waste heat or coal. Okay, so what happens in generator? This ammonia is separated from water. So whatever gases ammonia is here, gases ammonia is passed to the condenser. It will eject the heat to the atmosphere. Okay, then it will pass to the receiver. Then we have an expansion valve in which the pressure is reduced. So we have a liquid ammonia, liquid plus vapor ammonia, or liquid ammonia entering the evaporator. Inside the evaporator, it will extract the heat. So it will gain some latent heat, so that the liquid form is converted into gaseous form. So outside the evaporator, we have a gaseous ammonia. So that is the circuit of refrigerant. Again, in generator, what is happening? Ammonia is released and water is separated. So water coming outside, it is called as weak solution. Why it is called as weak solution? Because it has very less concentration or percentage of ammonia. So it is passed through the pressure reducing valve. Why it is passed through the pressure reducing valve? Because we have a generator which is a higher pressure because of pump. So in order, while entering the absorber, we want to make sure that it is entering at the pressure of absorber. So pressure reducing valve is used. So after that, that weak solution will pass to the absorber. In that way, this absorber circuit will complete, and outside is ammonia or refrigerant circuit. Okay, so we have to deal with two circuits: absorbent circuit and absorbate circuit. So I hope with this revision you remember that some points which we already discussed. So this is processes so which I just explained. Then one more diagram it is shown here. In this case, we are passing the heat or supplying the heat to the generator with the help of a solar collector. So see here, I'm not depending on electricity. Simply with the help of solar collector, I can pass the steam or I can pass the high temperature water through these coils. Okay. So if you practically what will happen, if you want to supply the water, a small pump will be needed near the solar collector. Okay, so practically we have to go for a small pump, again which will depend on the electricity, but main objective is to reduce that dependency on the electricity. Okay, then what are the requirements of a VRS? So in VRS, that there should be higher solubility. That means that ammonia or whatever absorbate we are using, that should have highest solubility for the absorber whichever we are using. So in one of the slides you'll see today what are the mixture we can go for in VRS system. Then boiling point, so there should be a very large difference between boiling points of absorber and absorbate. So you see here of the order of 150 degrees Celsius to 200 degrees Celsius. Higher the better. So higher should be the this boiling point temperature difference. So then we saw the differences between VCRS and VRS. So this is the simple VCRS. And this is a simple VRS. So whatever compressor part here in VCRS, we are replacing that with absorber, pump, and generator. So I hope this diagram clarifies your thoughts about the VRS. So if any interview, the interviewer asks you that why VRS better, or in which point of view that VRS is better than VCRS, you can say that VARS has very low dependency on the electricity. We are making use of solar energy, waste heat, and this is the first thing. And second thing is that the compressor is not involved in VRS, so there is a very less noise and less vibrations from the system. So these are two major points, and very that are sufficient to explain that why VRS, what are the features of VRS which differs it from the VCRS system. Then we saw some differences between these two. So in this case, COP is less for the VRS, and capacity 1000 TR we can achieve with a simple VRS system, but for the same capacity of 1000 tons, we have to go for a multi-stage system in VCRS. Then refrigerants, so there are various combinations in VRS that we'll see today. In VCRS, we can go for HFCs, okay. Hydrocarbons, or there are lots of refrigerants we have seen in the third chapter that we can go for in VCRS, hydrocarbons and hydrofluorocarbons. We cannot go for chlorofluorocarbons because these are being phased out because of their ozone depletion potential and global warming potential. Okay, so we also seen these advantages. So I will repeat this today. So advantages of VRS, advantages of vapor absorption refrigerant system. So in this case, only they are considered aqua ammonia. Aqua ammonia means water and ammonia. So ideally fits into the concept of integrated energy systems such as cogeneration involving combined generation, heat, refrigeration, and power on various fuels like biomass, coal, natural gas, heavy oil, solar, geothermal, etc. Okay. So wherever we are going for this integrated energy system, so where we are using this biomass, coal, natural gas, solar, geothermal, in that case, it is very ideal. It is excellent for waste heat utilization. So this is obvious. So it earns carbon credits, reduces taxes, promotes sustainable development. So this is very important point. So if I go for energy audit of any industry, so if I go for energy audit of this sugar industry, so in that case, what they study, this one of those point is carbon credits or carbon footprint. So how much carbon footprint that sugar industry is generating, or it is responsible for, that is being calculated. So if it is having less carbon footprint, so they will receive these carbon credits. Okay. So this carbon credits we also seen. Actually, we did not see this in classroom, but I have covered this in online lecture of our IC engine. So we have this topic last chapter of IC engine, that was emissions. In that case, carbon credit was one of the points. So if you do any effort in reducing the carbon footprint, that will be accounted in your carbon credits. So it reduces taxes and promotes sustainable development. So it uses best eco-friendly refrigerant, ammonia. So ammonia is a environment friendly refrigerant, but it is a toxic in nature. So if there is a leakage of ammonia in this chilled water system or refrigeration plant, it is very dangerous, and it is very toxic to the operators and the workers. And it has a wide operational range of 5 degrees Celsius to minus 55 degrees Celsius, but that limit is, there is a limit on this range. So if I go for VCRS system, so vapor compression, it can go up to minus 200 degrees Celsius also sometimes, or minus 150 degrees Celsius, but VRS has some limitations. Then it is having low maintenance costs because it is having no moving parts. So in VCRS we have compressor. Compressor means that it will have some moving parts. In VRS we have very less moving parts. So because we have pump, so pump is having some moving parts. We can say less moving parts compared to VCRS. And it can operate well for over 25 years. So its the durability is very good for VRS compared to VCRS. Okay. So this was the revision whatever we have studied in last lectures related to vapor absorption system. I hope I am able to recover all your those memories of our last lectures. Okay. So today what we'll do, today we'll analyze this VRS system in a thermodynamic point of view, and we'll calculate the COP. Then we'll solve the numeric. Okay. So those who have not drawn this diagram, they can quickly draw it because whatever derivation I'm going to do, it depends on this diagram. So let me connect my tab. Okay, friends, see in this diagram. So this is a diagram for a simple VRS. This diagram I have explained you earlier. So what we are interested now to carry out a thermodynamic analysis of this system. So speaking about the thermodynamics, we are interested in heat and work. Okay. So you can see in this diagram. So if I start with the evaporator, so let us start with the evaporator. We have a QE. Now what is a QE? QE is the heat absorbed from the space. Okay. Then next coming here, we have heat rejected. That is a QA. Okay. So from where this heat is coming, because the absorption is an exothermic process, so in that case heat is being generated and it is rejected to the cooling water. Then coming to the generator, we have here heat supplied, which is supplied externally, QG. Okay. Next we have condenser. So in condenser we know that the outer latent heat is being rejected to the atmosphere. So we have this QC. Okay. Apart from this, so this is related to the heat. If I talk about the work, so in this case only pump, we are supplying work to the pump, so that we have here pump work, that is a QP, right? So can anybody tell me what will be the this equation of first law, like according to first law? So first law we know that is a law of energy, law of conservation of energy. So can anybody tell what will be the equation according to first law? So all these values are in front of you. So we have heat values here, QV, QA, QG, QC, and we have work here, which is a QP. So by looking at the diagram, can anybody guess what will be the equation according to the first law for this system? Yes. So I'll repeat the question. Whatever heat and work interactions are there on the screen, I have also noted it down here, heat and here work. So according to the first law of thermodynamics, so what will the equation for this system? Okay. So by first law, you know that first law of thermodynamics, which is generally written as Q is equal to U plus W. Okay. Or generally we can write it also as a Q is equal to Q minus W. So whichever equation you want to do, you can write here. And we can assume this as a closed system, okay, though it is there is continuous flow, but as a whole we can see it as a closed system. So yes, any answers? So what will the equation for this system according to the first law of thermodynamics? So first law is the law of conservation of energy. So all this energy, quantity of energy, it should be conserved. So it can change from one form to another, but whatever total amount of energy in this system, that must be conserved. So any answers for this? You can type in the chat box. I will wait. Okay, I have one answer given by Rohit. That is U is equal to QE. QE, why you have taken positive? I don't know. Then minus QA. Okay, okay. QE will be positive. Yes. QG will be positive. Yes. Minus QC, that will be negative. Minus QP. Okay. QA. See, you are very close to answer. I can say you are very like 99% close to the answer. But one thing is there in this system. So like I said, as a whole, you can assume it as a closed system. But you have to also look for the temperature changes. So all these temperature values in this system, we are assuming as constant. So whatever cooling water coming from this way, this temperature is constant. Living temperature is also constant. So there is no transient phenomena like we are considering, and there is no temperature change over a certain period of time. So that change in internal energy, will assume it as a zero because there is no temperature change over a time period. So in this case, this whole diagram we can reduce to this schematic. So in this case, we have a VRS system. Okay. So like Rohit said, yes, QE, that is heat is been extracted with the help of evaporator that is added to the system. So we know that heat, about the heat, if heat is supplied to the system, that will be positive. Heat is rejected by the system, that will be negative. Work done by the system, that will be positive. Work done on the system will be negative. So that you know already. Then next is heat supplied in the generator. So that will be again positive. So this will be positive. This will be again positive. Now next is pump. So work done is on the system. So on the system work is always negative. And then this is the heat rejected by the system. So this will be negative. Okay. So you can see this as a account statement. Okay. जर तुमच्या इथं अकाउंट हीट तुमची अकाउंट आहे, जर तुमच्या खात्यात पैसे जमा होत असतील तर ते पॉझिटिव्ह झाले, खात्यातून पैसे जात असतील तर निगेटिव्ह. वर्क तुमच्यावरचं तुम्ही लायबिलिटी कन्सिडर करू शकता. तुमच्या जर एखादी लायबिलिटी टाकली तर ती निगेटिव्ह असेल, तुमच्या जे लायबिलिटी कमी झाली तर ते पॉझिटिव्ह असेल. इन दॅट वे यू कॅन डू द अनालॉजी. ओके. सो अकॉर्डिंग टू first law, so you can draw the system. You can show this four parameters. So here it is the evaporator, here it is a generator. Okay, then we have pump, and here it is the atmosphere. So what we have done here, whatever temperature of absorber, it is assumed to be equal to temperature of condenser. So there is a small assumption is being made. So that will be equal to, that you have considered as a TO, that is the outside atmospheric temperature. So according to the first law, this will be QG, sorry, QG, and then will be QE. Then we have minus QA plus QC. Then we have minus QP is equal to 0. This is the equation number 1. Okay. So according to first law, this will be the equation. See, the thing is here that this QP, that is the pump work, is very less compared to other values. So we have to neglect that. So neglecting pump work. Okay. And assuming, so this term we can assume as a QA plus QC. We can replace it as a Q capital C. So this is small c, here is a capital C, QC. So see, the equation will reduce to let us say okay, so this will be QG plus QE minus QC. QP will be 0, so that will be 0. So this will be equation 2. So we have neglected the pump work, and they have replaced this absorber plus condenser heat rejected by simply QC. Okay, so write it down. Okay, so in order to reduce your confusion, I will write here it as a condenser. Okay, condenser. So this is the absorber heat plus condenser heat. This will replace with simply QC. Okay. So that was related to first law. Then coming to the entropy point of view. So we'll just revise it. I know it's been a long time you have not read about entropy. So entropy, as you know, it is a degree of randomness. Entropy, this whole sub concept is not just limited to thermodynamics. It is applicable to even history, arts, geography, all wherever chaos is there. Okay, chaos. In that case, that chaos is supposed to be happen due to entropy. So we'll limit our discussion to only thermodynamics. So according to the Clausius inequality, so Clausius inequality, we know that for a cyclic process, this dq by t is always less than equal to 0. So it will be equal to 0 when that all the processes in cycle are reversible. If they are irreversible, that will be less than 0. So this is for a cycle. If I go for a processes means one-way processes. In cycle, we know that there will be like this diagram you might have studied, the 1 to 2. So it will go by path A. It will return with path B. So this is what we are calling it as a cycle. If I consider only 1 to 2, that will be a process. So in case of processes, you know that relation is ds is always greater than equal to dq by t. Okay. Then for reversible, this ds, change in entropy. ds is nothing but smallest change in entropy. This is equal to dq by t. Generally, it is also written as delta S is equal to delta Q by temperature. So this is reversible. For irreversible, so pay attention. This is very important. Entropy chapter you are studying in thermodynamics, but today I'm taking its revision. For irreversible, this ds will be always greater than dq by t. Okay, so change of entropy always be greater than change in heat transfer divided by the temperature. So integrating will get so integrate on both sides. So this will be integration ds greater than integration dq by t. So let us say 1 to 2, and this is a 1 to 2. Okay. So integration ds, that will be s, and from 1 to 2, that will be s2 minus s1 will be equal to, or sorry, not equal to, this will be greater than, this will be greater than integration 1 to 2 dq by t. To balance this equation, we have to introduce the entropy of generation. So s2 minus s1 will be equal to integration 1 to 2 dq by t plus entropy of generation. So then you might remember that we have studied this concept of entropy of generation, that entropy in the universe always increases. So that is, this entropy of generation is always greater than or equal to 0. So this is equal to 0 in case of only reversible processes. In case of irreversible processes, it is always greater than 0. And by logic, or in generally all the processes in the universe are said to be irreversible. So that means that entropy will always increase. So this is the entropy of generation. So with this small recap or revision, we'll move towards our derivation. So applying Clausius inequality. So first we'll assume that assuming all the processes in given VRS system are ideal, or in other words, I will say reversible. Assuming all the processes in given VRS as ideal / reversible. So if I apply the Clausius inequality, so applying Clausius inequality. So we know that ds this integration dq by t will be equal to 0. So how to represent this in our case? So see here in this diagram. I'm very sorry. Some problem is there. This PPT. So if you see here in this diagram, what is happening? Qg, amount of heat, it is being transferred with at the temperature Tg. Okay. Then we have QE, so plus QE, which is transferred at the temperature of TE. Then we have this QA plus QC, that is a QC, which is transferred at the temperature TO. So that is a minus QC divided by TO. Okay. And this, if I neglect the pump work, so this will be equal to 0. So this will be our equation if I consider the Clausius inequality. So I think that last derivation is gone. I cannot trust this softwares. Okay, anyway, I'll write again. Applying Clausius inequality for Q1 VRS. So in this case, that will be Qg divided by Tg plus Qe divided by Te minus Qc divided by To is equal to 0. In other words, I can say here it can be written as Qg divided by Tg plus Qe divided by Te is equal to Qc divided by To. Now from the first law, so here we have written here, you can see here Qc, you can write it as a Qc is equal to Qg plus Qe. Okay, so this I can write again as divided by Tg plus sorry, not Te. So this will be Qe. This will be Qe divided by Te. Qc is what we have written there. It as a Qg plus Qe divided by To. Okay, so I will take all that Qg terms on one side and Qe terms on one side. So another side. So this will be Qg divided by Tg minus Qg divided by To. So this term I have separated and I have taken out this only Qg by To term on the LHS. This will be equal to Qe divided by To minus Qe divided by Te. Okay. Now this I will take Qg as common. This will be equal to 1 divided by Tg minus 1 divided by To is equal to, remember To is the temperature of atmosphere. In this case, we assume that temperature of absorber and the condenser are same, that is a To. Here I will take out the Qe, that will be equal to 1 divided by To minus 1 divided by Te. Okay. Now, if our main objective in this case is to calculate the COP. So COP will be equal to, what is our objective? Our objective to extract the heat from the space. So that is the QE. And what is our input? In this case, our input is pump plus generator heat. So if I neglect the pump heat, so see here, input will be equal to, I'm applying some pump work. So that is a QP plus I'm supplying some heat in the generator. So that will be Qg. So I will neglect this pump work. Okay, so this will be divided by Qg. So that is the formula for COP in this case. So, okay. So by looking at this and by looking at this, you might have already concluded that I have to take Qg as the denominator of QA. Okay. So I'll do that. I'll divide both sides. So first of all, I will write this equation number. So this will be 3, and let this be 4. Let this be 5. So divide equation 4 by Qg. So this will reduce to 1 divided by Tg minus 1 divided by To is equal to QE divided by Qg into 1 divided by To minus 1 divided by Te. And this is nothing but your COP. So what I will do in next step, I will keep this on one side and I will transfer this on another side. Okay. So in next step, I will first reduce these terms. So I hope you have written this. I'll wait for 1 minute so that you can write. Okay, so I hope you have written this equation. So in next step, we'll solve this. We'll simplify this equation. Okay. Okay, I'll add one more slide here. Okay, so this it was 1 divided by Tg minus 1 divided by 1 divided by To. It was equal to QE divided by QG in bracket 1 divided by To minus 1 divided by Te. Okay. So first we'll simplify this term LHS. So this will be To minus Tg divided by Tg into To is equal to QE divided by QG. Here in bracket it will be Te minus To divided by To into Te. Okay. So our objective is this term, that is the QE divided by QG, which is nothing but the COP. I will keep this on one side. So this will be QE divided by QG on one side. So what will I will do? I will transfer this to the LHS. So how I can transfer this? First I will write the LHS, that is already To minus Tg divided by Tg into To. This into, so if I want to transfer this on this side, I have to divide there. So divide means its denominator will become numerator, its numerator will become denominator. So this will be reduced to To into Te divided by Te minus To. Okay. So in this case, you can see this To and this To will cancel because one is in numerator, another is in denominator. This will reduce to To minus Tg divided by Tg into, this will be Te divided by Te minus To. Okay. Another way I can write this. So this will be COP. So this is, all the processes are assumed to be reversible. So whatever COP will get, so that will be a maximum COP, or you can say a reversible cycle COP. So I'll rearrange some terms here. I will multiply numerator and denominator by minus 1 divided by minus 1. So this will reduce to Tg minus To divided by Tg into in bracket here Te divided by To minus Te. So this will be your relation of COP with temperatures. Okay. So write it down. Okay, so ED's compressor has already sent the link, as Rohit is saying. So please write it down up to COP, and maybe tomorrow I will take a lecture in which we'll solve one example which is related to COP. Okay, so I think there are huge gaps are there between one lecture and the next lecture. So what I will do, I will keep 2 hours lecture for every subject till your this training and placement activity goes. I think that will go up to September end. So up to September end, what we'll do, like we'll keep 2 hours lecture for one faculty daily. So if I'm taking today, so today I will take 2 hours of RAC. Next day, ED or OR will take 2 hours. So that way there will be continuity in the syllabus. Otherwise, what will happen? I will take 1 hour. Then after 4 days or 5 days, again I will take 1 hour. So that link between two lectures breaks. Okay. So anyway, right up to this COP and then we can conclude. Okay, so I'll give some 1 more minute and then we can conclude. Okay, so I hope you have written this. I'll close the window. So quickly I will take the attendance also.